Do you wonder why in chemistry the compound CO2 is named as carbon dioxide, but the compound CaF2 is called calcium fluoride, not calcium difluoride, although in both cases the second element has two atoms? Why is there this ambiguity in names? Mastering the nomenclature, formulas, and structure of inorganic compounds is essential for a good understanding of chemistry. Whether you are a student grappling with naming conventions or an enthusiast seeking a clear refresher, this video will guide you through these core concepts with ease. Through a step-by-step approach, this video simplifies the process of learning, making it accessible and engaging even for beginners. Hi everyone, this is Akhilanand Singh. This introductory video on chemistry discusses nomenclature, formulas, and structure of covalent compounds. The periodic table of elements is a fundamental tool in chemistry. It is essential for understanding the nomenclature, formulas, and structure of compounds as well. Most elements in the periodic table are metals categorized into distinct groups. The first column or group of the periodic table, excluding hydrogen, consists of alkali metals, while the second group contains alkaline earth metals. The central block houses transition metals, followed by post-transition metals and metalloids to their right. On the far right, approximately 12 non-metal elements are found. The final column contains noble gases. Classifying elements as metals or non-metals is crucial, as their interactions determine the types of chemical bonds formed and also the resulting compound names. Metal-metal interactions produce metallic bonds. Metal and non-metal interactions form ionic bonds. Non-metal interactions create covalent bonds. Majority of compounds in inorganic chemistry are formed by either ionic bonds or covalent bonds, and very different and distinct naming rules apply to them. Before talking about compounds and their names, we must know about a very important and almost universal rule called the octet rule. The octet rule states that, barring some exceptions, almost all atoms tend to gain, lose, or share electrons with other atoms to achieve a stable configuration with 8 valence electrons, resembling the electronic configuration of noble gases. Noble gases already have stable configurations, 2 electrons for helium and 8 for others. They are generally inert, they don't need to form bonds to achieve stability. But there are some exceptions to this rule. Hydrogen aims to form a duet because its nearest noble gas helium has only 2 electrons. Transition metals often achieve stability with 18 electrons. Sometimes elements like boron and aluminium form compounds with fewer than 8 electrons, and elements phosphorus, sulfur, chlorine, arsenic, selenium, bromine, etc. accommodate more than 8 electrons in the valence shell. Having covered the octet rule, let's now begin with covalent compounds. Bonds among nonmetals are covalent bonds where atoms share electrons with one another to attain the stable octet state. The most basic covalent compounds are created using atoms of only two nonmetals, and they are called binary covalent compounds. In examples that follow, we explore the nomenclature, chemical formula, and Lewis structure of various such compounds. But before that, it is crucial to understand the three naming rules for binary covalent compounds. The first rule for naming binary covalent compound is the order rule. In a compound, the element with the lower electronegativity is named first. An easier way to predict electronegativity is that it increases as we go from left to right and bottom to top in the periodic table. An arrow from the bottom left to the top right indicates increasing electronegativity. Francium is the least and fluorine is the highest electronegative element in the table. The second rule is related to IDE suffix with the second element. For example, if the second element of the compound is chlorine, it will be named chloride. If the second element is oxygen, it will be called oxide. If it is sulfur, it will be called sulfide, and so on. The third rule is related to the use of prefixes. To clarify the number of atoms in a molecule, we should use prefixes like mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Though both elements in a compound may use prefixes to indicate the number of atoms, an exception applies to this rule. The prefix mono is omitted for the first element. Reason for using prefixes. Non-metals have ability to combine in multiple ratios, for example CO, CO2, N2O and N2O4. So prefixes like di, tri, etc. are essential to clarify the exact composition of elements in the compound. Let's discuss the compound CO2 as our first example. The chemical formula indicates the presence of one carbon atom and two oxygen atoms. As both carbon and oxygen are nonmetals, we can assume that they form covalent bond through electron sharing. Let's discover how the atoms establish the covalent bonds. Oxygen is located 2 columns before the column of noble gases in the periodic table, and we know that all noble gases have 8 valence electrons. So oxygen will have 8 minus 2, that is 6 valence electrons. Similarly, carbon is 4 columns before the noble gases, giving it 4 valence electrons. In the Lewis structure, one carbon atom is positioned centrally, flanked by 2 oxygen atoms, each represented with 6 dots for their valence electrons and carbon with 4 dots. To achieve a stable octet, the carbon atom shares 2 electrons with each oxygen atom, forming 2 double covalent bonds. This allows all 3 atoms to attain 8 electrons. Each double bond consisting of 4 shared electrons is depicted as 2 lines between the carbon and oxygen atoms. Naming the compound CO2. Since carbon is less electronegative than oxygen, it will be named first. In a covalent bond, we need to use prefixes to indicate the number of atoms, and the second element always ends with the suffix IDE. We must also remember that the prefix mono should be omitted if it applies to the first element. Based on the above rules, the correct name for the compound CO2 is carbon dioxide. Example 2. Let's understand the covalent bond in the compound CO. If carbon and oxygen atoms share 2 electrons each, totaling 4 shared electrons, oxygen will achieve its octet, but carbon will be left with only 6 electrons. To complete carbon's octet, oxygen shares an additional pair of electrons with it, forming a triple covalent bond. This results in both atoms attaining 8 electrons in their valence shells as depicted in the Lewis structure, with 3 lines between carbon and oxygen. This is a special case of covalent bond called coordinate or dative covalent bond, where a single atom shares both electrons in the bond. CO is named carbon monoxide. The prefix mono is used for oxygen to indicate one atom, while it is omitted for carbon, the first element, as per covalent naming conventions. Example 3. Chlorine monofluoride. In this example, we start with a compound name. From name we derive the chemical formula and then draw its Lewis structure. The name clearly indicates one chlorine atom and one fluorine atom in it. This leads us to the chemical formula ClF. To create the Lewis structure, we represent the chlorine and fluorine atoms with their valence electrons, 7 each. As both are in a group of periodic table, just one column before the noble gases. By sharing 1 electron each with 1, both atoms achieve a stable octet of 8 electrons. In the Lewis structure, a single line between the atoms represents this covalent bond, with each atom surrounded by 6 unpaired electrons. Example 4. Our next example is chlorine trifluoride. Its name indicates 1 chlorine atom and 3 fluorine atoms, giving the chemical formula ClF3. To draw the Lewis structure, we place the chlorine atom centrally, surrounded by 3 fluorine atoms, each represented with 7 valence electrons. Each fluorine atom shares 1 electron with chlorine, forming 3 single covalent bonds, depicted as lines between chlorine and each fluorine. This allows each fluorine atom to achieve an octet. However, chlorine, the central atom, ends up with 10 electrons, 7 valence electrons of its own, plus 3 shared from fluorine. Is it incorrect? No. It is valid because ClF3 is a hypervalent molecule where chlorine, as an element belonging to the third period of the periodic table, can accommodate an expanded octet using its d orbitals. Example 5. The next compound with the chemical formula H2O is commonly known as water. Let's derive its chemical name. Both hydrogen and oxygen, being nonmetals, form covalent bonds. The compound follows the naming rules for binary covalent compounds. With lower electronegativity value, hydrogen will be named first. With 2 hydrogen atoms and 1 oxygen atom in the formula, the compound is named dihydrogen monoxide. To draw the Lewis structure, we place the oxygen atom centrally, flanked by 2 hydrogen atoms. Oxygen has 6 valence electrons depicted as 6 dots, while each hydrogen has 1 valence electron shown as 1 dot. Each hydrogen shares its electron with oxygen, forming 2 single covalent bonds. This allows each hydrogen to achieve a stable duet of 2 electrons and oxygen to attain an octet. The single oxygen atom also retains 2 lone pairs of electrons. Example 6. The next compound has the chemical formula N2O. Let's work out its chemical name. Since its constituent elements nitrogen and oxygen are nonmetals, they form covalent bonds. The compound name adheres to the nomenclature rules for binary covalent compounds. With 2 nitrogen atoms and 1 oxygen atom in the formula, the compound is named dinitrogen monoxide, also keeping in view the electronegativity of nitrogen, which is less than oxygen. To draw the Lewis structure, we place the two nitrogen atoms one after another, followed by one oxygen atom. Nitrogen atoms have 5 valence electrons, depicted as 5 dots around each, while oxygen has 6 valence electrons, shown as 6 dots. The two nitrogen atoms share 3 electrons each, forming a triple covalent bond, allowing both nitrogens to reach a stable octet. The nitrogen atom near oxygen then shares 2 electrons with it, forming a single covalent bond, enabling both achieving their stable octet of valence electrons. This is another example of dative covalent bond where one atom donates and shares both electrons in the bond. Example 7. Our next compound is N2O4. This time as well, nitrogen and oxygen, both being nonmetals, form covalent bonds, and the compound name will follow the naming rules for covalent compounds. With 2 nitrogen atoms and 4 oxygen atoms in the formula, the compound name is dinitrogen tetroxide. For Lewis structure, we place the 2 nitrogen atoms one after another in the center, flanked by 4 oxygen atoms around. We depict 5 valence electrons as 5 dots around each nitrogen atom and 6 dots as 6 valence electrons around each oxygen atom. This compound has multiple covalent bonds. 2 central nitrogen atoms form a single covalent bond with one shared electron each. NO bond. Each nitrogen forms a double bond with one oxygen, and it also forms a single bond with another oxygen. Our next two examples deal with homogeneous diatomic molecules formed by 2 atoms of a single nonmetal element. The bond between the 2 atoms are covalent, but they are not named as regular binary covalent compounds. While naming, we simply attach the word molecule after the element name. Let's see the bond between 2 chlorine atoms in a chlorine molecule. Both chlorine atoms having 7 valence electrons share 1 electron to form a single covalent bond, achieving a stable octet. Example 9. In the oxygen molecule, each oxygen atom shares 2 electrons with the other, forming a double covalent bond. This allows both atoms to attain 8 electrons and a stable energy state. That's all for this video. We learned how two non-metal elements combine using covalent bonds by sharing one or more electrons to reach a stable state. We also learned how covalent compounds are named. I'll see you later in the next video where we discuss ionic compounds. Thank you.